Okay, so now let's do the following. Suppose the surface S is defined by the graph, or defined as the graph of the function g of x comma y equals y squared e to the x for 0 less than or equal to x less than or equal to 10 and 0 less than or equal to y less than or equal to 12. Suppose also that the density at any point x comma y comma z is given by rho of x comma y comma z is equal to the fraction xy over z plus 3. Okay, so let's see. Let's just finish the question before making some comments. Then we'll set up, but do not evaluate. Do not evaluate an integral representing the mass of capital S. So I think two comments are in order. First of all, this density function that we are given, it seems to just apply to any x comma y comma z, and that's fine. Even imagine something like this function includes a lot of information, the density at every point in three-dimensional space, but what we want is just the mass of a certain portion of it. So it's given by this like piece of tinfoil or something that's just part of the three-dimensional object, and that foil is the graph of lowercase g, and that surface, capital S, is what we just want to know the mass of that portion of this three-dimensional object. That's maybe the idea behind this. The other thing I guess just to comment on is we talked about taking a provided density function and computing an integral in the parameterized surface situation. We haven't done it here when S is described instead as the graph of a function, but this is really a nice mixing together of ideas in a way that's going to work out. So I don't think any of the particular steps are going to be surprising, but we're sort of like filling in that last piece of the skill chart or something like this here. So the parameter domain here is capital D equals, well, how about x going from 0 to 10 and y going from 0 to 12? So I'll just write this as a Cartesian product. D capital S is going to be 1 plus, we need the partial derivative of g with respect to x, and then the partial derivative of g with respect to y. So when you differentiate y squared e to the x with respect to x, well, you copy the y squared coefficient, and then e to the x differentiates to itself, and then squared. And then we need the partial derivative with respect to y. So now we copy the e to the x constant, and then the y squared differentiates to 2y, okay, and then squared. And then this will be d capital A, so dA, or we can just do dx dy or dy dx. Oftentimes you might see that you just write a dA if you're unsure, but since we're just we see constants as bounds both for x and y, we can just go ahead and do a dx dy here. So then the mass should be the double integral over the surface S of the function rho of x comma y comma z d capital S. This rho again is just playing the role of the function that we've been calling lowercase f. Now, in terms of actual implementation for us, yeah, integral sign, leave a little bit of space, integral sign. Since we know at the end we're going to write dx dy, so y is on the outside, so 0 to 12, and then the inner integral will go from 0 to 10. Now we need rho. We should write this here, except we need to be sure to not just write xy over z plus 3 directly. xy is fine in the numerator. Z does need to get substituted. Yeah, that's that same issue. If we write a z here, we'll have an integral that has x's and y's and z's. So we need to replace the z with g of x comma y. So y squared e to the x there, then plus a 3. Okay, and then the ds gets replaced with what we had right here. So we'll have root 1 plus quantity y squared e to the x quantity squared plus in parentheses 2y e to the x close parentheses squared, and then dx dy as we had already decided we were going to do. Okay, we're done with this problem, but what I'd like to do is go through a preview flowchart. Alright, you are kind of already noticed a little bit of the mix and match nature of the things that are going on, but to help clarify, because this is a challenging topic, there is a handout. So start with a surface S. Now S can be described one of two ways. Either S is described using parametrization or parametrically, or S could be described as the graph of a two input variable function we'll call lowercase g of x comma y. Now if S is described parametrically, that means that the description of S looks like this, right? S is parameterized by a vector function r of u comma v, and it has components x of u comma v, y of u comma v, z of u comma v, with u v belonging to capital D, a parameter domain. And then that capital D, the parameter domain, is u from a to b and v from c to d, perhaps in its most basic format, but you might actually have that one of the bounds is written as a function of the other parameter. So you might have u is stuck between two constants a and b, and then v might be stuck between two functions of u, for instance, or the other way around. ds is the magnitude of the cross product of partial derivatives of this vector function version of the parameterization times a dA, where dA is either du dv or dv du. Now, just to follow the other track, if S was instead described as the graph of a function, right? So if S is the graph, so in the gray box in both cases, you see the description of S. So if S is described as the graph of a function, g of x comma y, but not probably the whole function, because if it goes on forever, your integral would go on forever, and that'd be, I guess, some version of an improper integral. Let's not go there right now. And then the parameter domain, capital D, it should just be, well, bounds for x and y. So it's really, in the end, to use more geometric language, it's the projection of the surface onto the xy plane. So it's the relevant part of the domain of G that you'd like to integrate over. And then ds, it's really just, this is just this radical and so on that you're seeing here is just a special case of what's over here. So ds is root 1 plus partial derivative of g with respect to x, then squared, plus the square of the partial derivative of g with respect to y, then times a dA outside the radical, and dA is either dx dy or dy dx in its nice cases. Again, here, even here, dA is du dv or dv du, but maybe, depending on the parameter domain, you might end up switching to polar or something like that, either over here or over there, but that's a more complicated thing for later. So once you have those pieces of setup ready to go, once you have all these ingredients, now we're ready to integrate the function lowercase f, a provided function, I hope, over the surface S ds, but only if we know what f of x comma y comma z is, right? So you've got to have a function, a scalar function, or a scalar field, lowercase f of x comma y comma z, ready to go. So what is it? What do you want to compute, right? So if the question already gave you a function lowercase f to integrate, then great, use that. If you were just asked to find the surface area of the surface capital S, then you might have to build the function yourself, and it's just f is the constant function whose output is always 1. That brings up how what we're talking about right now as a special case is the type of integral we set up in the previous section. If you are asked to compute the mass of the surface S, then for the function f, you just need to use the provided density function. Then, now that you know what lowercase f is, you take that, now you have your function, and you integrate f over the surface S by plugging in for f and for ds and integrating over d based on what we had up here in the gray, in the pink box and in the yellow box. Yeah, so you'll have to substitute the components of the parameterization written as a vector function if s was defined parametrically, and if not that, you'd have to substitute for every z a g of x comma y if instead s was described as a graph of a function. That way, you only have the variables that show up in the dA, right? So the integral that you eventually set up should only have u and v as variables or x and y as variables. If you have more variables, you need more substitution to be done. Then you can evaluate this double integral over d now of whatever stuff, it's going to be messy, dA, where dA is either dx dy, dy dx, or du dv, dv du, and if necessary, you might do some variable substitution to polar coordinates, or you might do some custom substitution using Jacobian type stuff. So this is quite a lot to deal with. If we just zoom out a bit for this overview, you'll notice that the way this PDF is set up, there's actually a lot of empty space right here. That's intentional because this is going to get filled in a little more next time.